I want to do. Okay. So now I'm screen sharing. Shouldn't it say I'm recording somewhere?
Buttons there, little red flash.
Where is it?
It's recording. It's recording.
It is, okay. Where do you see the button that's a little red flash?
The flashing red is behind.
On the green bar, like the second one.
This one?
Yeah, like that.
Oh,
little red thing.
it's not flashing.
It's flashing.
It is?
Yeah.
Jesus Christ, I'm old and decrepit, man. I can hardly see anymore. All right. So good. Okay. We're off and running. You know what? I'm going to get my glasses out. I'm going to need them. Yeah, we're going to be talking about, yeah, Timothy, you can hear me okay? Oh, well.
I can hear you perfect.
Okay, and let me know if you can't hear the music when I start it too, but we'll get going first, okay? Let's see now. Oh shoot, I forgot to transfer these things into my my Windows, but I'll do that in a minute. Okay, we're going to start right off with a really interesting chaotic equation, okay? And let me get Max MSP going here. And let's bring up, say, RTC mix tilde, and I'll make it be stereo just for fun. All right. This equation is called the logistic map or the population equation, okay? And it's really, really intriguing because it's actually very, very simple, okay? But it also has kind of at its heart how all these things work, okay? And the basic equation is x equals, oh wait, I need to make that a little bit bigger. Okay, x equals r times x times 1 minus x. Okay, pretty simple, straightforward equation, right? Here's the trick, okay? Actually, I should make this lowercase x. To get chaos to happen, you have to do this thing called iteration. Okay, and that means you're going to run the thing over and over and over again. Well, what do I mean run it over and over again? Well, you're going to start out with a value of x that you just choose randomly, and you're going to put it in this equation for x here, and you're going to choose a value of r, and you're going to compute the equation once, and you'll get something out of it. Then you take that something you got out of it, put it back in for those x's, recompute it again, and you'll get something out of it. Okay, so it's almost what we call a recursive procedure in a way, okay? Because you're constantly taking the output of the equation and putting it back into the equation. And you do this like 1,000 times or so, and really interesting things happen as a result, okay? Well, let's set it up and look at it and see what are those interesting things, okay? All right, well, I'm going to open up my RTC mix and put in the equation. I'm going to say x equals r times x times 1 minus x, okay? And I'm going to do that iteration thing. I'm going to say for, we all learned this last time, I equals 0, I is less than, say, 1,000, okay? I equals I plus 1, and we're going to do it up. We're going to do it. And that should take care of it, okay? And we're missing some stuff. First of all, we need to have a value for r, and we need to have a value for x, okay? Now, I'm going to just say, let's choose a random value for x. And I'm doing something slightly wrong here, but I'm going to explain that later. So I'm going to say x equals random, okay? And random is one of those RTC mix functions that I'm not going to bother to look up the documentation tonight, but it returns a number between 0 and 1. So that'll just give us an initial x value. And then this, by the nature, it's going to compute x, do it again, and put in, the clever thing about these computer languages is that they will compute that on the right-hand side of the equal signs before that. So it's not going to put the x in here, it's going to put the x in there and then do it, okay? Now, the other thing we need is a value for r, all right? And this is, I'm going to teach you something new about RTC mix, okay? I'm going to say r equals $1. This is a way of getting data into the RTCMix object from the outside world. And when we start working with Unity and others, we're going to be having to send it data like, where is this object? Who's looking at this object? What is the object doing? Things like that. So you can have these variables labeled $1, $2, $3, and bring it in. Well, how am I going to bring it in? Well, first of all, let me save this, because if it crashes, I don't want to have to redo it all. Okay. Save. Okay. And we will go to soft fall week 3, and I'll call this class pop 1. Okay. Right. The reason I forgot to mention, the reason it's called the population equation is because it's supposed to mimic the fluctuations in populations between predator and prey, and R has to do with the amount of resources available. Okay. Again, it's called the logistic map because it's called that. Basically, I don't know. Okay. So how are we going to get R in here? Well, we're going to do this. We're going to say, we're going to create a floating point number generator out here. Okay. It's locked. Okay. F. All right. And that will put out, let me just do a print here. Shoot. If you want to see what it does, print objects are very useful in MaxMSP. Watch this over here. Basically, that just puts out floating point values, okay? Which is what I want to have for R. Now, I'm going to have to be very careful, because it turns out that R between 0 and 2 doesn't really do anything. It just turns it into a 0. Between 2 and 3.99999, interesting stuff happens. But if I go to 4, it crashes the equation. The equation will go to infinity, and we can't actually see infinity. Well, maybe some of you can. All right, so we're going to take this. Now, how do I turn it into that R equals 1 value? Well, I do this. I'm going to use a max object called prepend. If I can learn how to spell properly, var1. What this is going to do is this is going to change this single number into a message that looks like this. See, it says var1 0.142, var2, things like that. Well, that's actually what we want, because RTCMix will see this thing that says var and go, oh, it's a variable from outside, and it's variable number 1, $1, and that's the value. So that's how we're going to get R into this thing, okay? All right, now, so we have it happening, but how do we see the results? Well, there's 2 ways to do it. There's a not so good way. I can actually say here, print X, okay? And now it'll run, okay? Oh, the other thing that I forgot to tell you is RTCMix, even if you're not doing any audio with it, always has to have the digital to analog converters turned on, because it runs off that, okay? So when I turn this on, okay, and I start putting in my R's, oh, it's not printing. Why not? Take this off. Oh, that's because, remember I said you have to trigger the script, okay? So let's put in R value. Let's put in an R value of, say, let's put in an R value of 2.4, okay? Right about there. Okay, now I turn this on. Now, okay, there it is. Unfortunately, this is what we're seeing as a result of the print statement. And yeah, you can see it, and it's going to kind of work, but it doesn't really make it easy to see, and especially if I want to see that value out in my max patch. So I'm not going to do that. I'm going to do something different. Remember we had that thing called max bang that would send the bang around to the RTCMix? Well, there's also a special object instrument called max message. And you give it a time, and then you give it the message you want to send out. In this case, we want to send out X, because we want to see the value of that X, okay? So let's save this. And now, out of this this is stereo, so that's the left audio output, the right audio output, and that's where the bangs come out. But also what comes out of here are those max message numbers. So I'll put it there. Right. And now, let me see if I'm doing this in the right order. Yeah. Yeah. Okay. So here we go. Set this up to something, say 2.41. I hit bang. And look, 585. And remember I said that up to about 3, well, I didn't say anything, okay? But it's bizarre because they're just putting in random numbers here, but they're converging on a single value of 0.585. So all of a sudden we're getting a hint, maybe something weird is going on. Well, let's increase our 2 here, and now what do we get? Ooh, 602. Isn't that weird? Yes.
Why can't it go over 4? Why does it crash over 4?
I'll tell you when we get to it, okay? Maybe we'll make it go over 4 just for fun, okay? All right. But notice that these are converging on a number, okay? Well, I'll just tell you now. If you go over 4, the number it tries to converge on is infinity, okay?
I'm a little confused on how do you move? Like it goes.
Well, normally this is going to go between 0 and 1,
Yeah.
okay? If you go over 4 with R, when you iterate the equation,
Oh.
it goes, oh my God, I'm going to infinity and beyond. So yeah, it doesn't happen. Okay, but now we get to 2.6, and now it's, ooh, single number. Let's goose it up to about, say, 2.99, okay? And what do we get? Ooh, 0.666. Ooh, it's an evil number, okay? Let's bring this up a little bit to 3 now. What do we get? Oh my goodness, something odd happened there. The more I click it, I get either 0.6 or 0.690 or 0.643. So all of a sudden, this equation, which was only giving us one value before, is flipping kind of randomly between 2 different numbers. Well, let's increase 3 a little bit more. Our R value is now going to be 3.127. Let's see what it's doing now. Ooh. Still going between 2 numbers, but they're farther apart, okay? This is a very weird equation, okay? Let me bring this up to like 3.2. Still 2 numbers. Let's go up to, oh dear. Fortunately, I didn't click on it. Okay, let's go up to 3.4. A little beyond 3.4, okay? Oh my goodness. Now you can't really tell, but it's cycling between 4 numbers now. Okay, we're going to see this. It's going to be much easier to see in a minute. And then if I go up to say something like 3.7, you know what it does? It enters chaos. Oh my God, the numbers aren't repeating at all. It's like chaotic. It's a chaotic equation. So this is a chaotic equation. The thing, well, let me bring up the version that plots it out, okay? And I'm not going to code this one up by hand because it'll take too long, and I did it ahead of time, so this will make it a little bit easier to see what's going on. Yeah, and let's see. Oops. Right. Okay. All right. So let me put this guy away. And let me go down here. I have this cleverly named directory called safety, where I've actually already built all this stuff, just in case things weren't working out in the class. And I got a little nervous. Oh, I am nervous. Okay, so I want to do, yeah, number 2. Okay, now I've added a bunch of maxi stuff. All this stuff down here, you don't need to worry about. This is just to plot out. And what we're going to do is we're going to plot R along here, and we're going to plot the values of X that come out along here, okay? And all this nonsense here is a way of changing the R value that goes from 0 to 3.99 to be between 1 and 300, because that's 300 pixels high, okay? And this one is going to take 0 and 1, which is our X values, and go between 300 and 1, because this guy is excuse me, the R value is here. This is 300 pixels wide and 300 pixels high, okay? And this is just a way of making a little bit of a dot that's going to have a red color to it, okay? I'm sending out 2 values with my max message because I'm sending out the R value and the X value. So what I have to do is unpack them, and the R value is going to come out that one, and the X value is going to come out that one, okay? All right, again, these are max MSP things, you can look them up. Up here is all the stuff we've already done, except now I've added a metro so I don't have to click the bangs by hand, okay? So let's start it out, okay? Let's start this out with maybe 2.1, okay? And here we go. And there it is, okay? Now, I'm going to do something right now. You see how it's like doing all this nonsense here? And you probably noticed that the last time. That can get annoying, especially if you're looking for some error messages or something like that. And in certain cases, it'll even slow down your machine a little bit because it's trying to print all this stuff. I can get rid of that by saying print off. And now it won't do that nonsense, okay? So let's get this going. Here we go. All right, I'm going to bring up the 2. Now watch what happens. Okay, as I increase R, remember the numbers were increasing until I got to about 3. Watch what happens. 2.7, 2.8, 2.9, 2.9. There, splits. Remember we're getting 2 different values? Yeah, now watch what happens if I keep going. This is hard to do with my mouse. Okay, right. And now it's going, it's going, it's going, it's going. It splits again. Remember, we're getting 4 values for a while? And then you keep on going, and it goes into, chaos. Oh my goodness. We can't tell what's going to happen. We just got to make sure we don't go above 4. Okay, but we'll get really close to 4. And that's what the logistic map looks like. Okay. Fun. Isn't that weird? I mean, this is weird. The equation is so simple, but and this is why people were really intrigued by this back in the when computer graphics first came to the fore in the 1980s, and they started seeing some of these things. They're just going, my God, what have we done? And they started exploring some of the stuff. We're going to look at 3 chaotic systems tonight, and each one we're going to sonify a little bit differently, because that's our next step, is obviously to sonify this. Okay, and we'll just do it right here. Okay, I'm going to open up the RTC mix, and we already have our values. We know what we want to do. I'm going to do something very simple. Okay, I'm going to say amp env equals make table line 1000 0, 0, 1, 1, 2, 0. Okay, so if you remember from last time, this is basically going to create an envelope made out of lines, and at relative time 0, it'll be at 0, and at relative time 1, it'll go up to 1, and then at relative time 2, it'll go back down to 0. So I got that nice fade up and fade down, okay? And that's going to stretch that for as long as we're going to use it, okay? And I am going to use it. I'm going to use it inside a wavetable instrument, okay? I'm going to start it at 0. I'm going to make... how fast am I going here? 10. Let's go 100. I'm going to make this be 0.2 seconds long, okay, with an amplitude of 10,000. And I'm just doing that because I know from experience. And now we have to choose our frequency, all right? Now remember, X is the thing we're going to sonify. And X goes between 0 and 1. So I can easily turn that into a frequency that we hear by just saying X times 1,000. Because between 0 and 1 will now go between 0 and 1,000. And 1,000 hertz is about, it's like an octave above middle C. Okay. So that sounds pretty reasonable, all right? And that's all we're going to do. We want to take, we want to take amp env and times amp env. I just made that 100,000, didn't I? That's a problem. It would have been like the heavy metal version of this. Okay, so again, this is review, okay? Remember, we multiply this envelope times our actual amplitude, and we'll get that nice fade up and fade down. And it will stretch it over, even though I have that going to 2, it'll fit it to within 0.2 seconds, okay? So let's do this. Save it first, let me clear this. And let's make our metronome. What the heck, It's fun to hear it kind of fast. let me go in and make this be only 1/10 of a second long, okay? And we're gonna have to scale this down a little bit. Let's make it be 5,000, okay? Because they're gonna kind of stack up on each other. All right, now, start it up. Let's get this going back down to say 2.7, okay? And we'll hear. Okay, we'll hear, let me look at my, options here. Audio status. There's the problem, okay? I think I want to go to Zoom audio device, don't I? Yeah. Okay, let me hear this now. Hopefully we'll hear it. No, I don't. Oh, actually, I did want to go to headphones. Why am I not hearing it? Okay. Start, duration, amplitude, pitch. Yeah. Let me see what it's printing out. Sorry, guys. If this doesn't work, I'm going to go to the one that I had pre-planned, okay? Okay. Nope, that's actually legit. Okay. Right. Okay. What am I doing wrong? It has to do with our Zoom setup, I'm afraid. Options, audio status. That should actually have worked. It's not. Uh-oh. Okay, I'm going to pause my recording and stop the share for a minute so we can get this kind of figured out. I go over here to Zoom. All right. Pause recording. Okay, we're back. And Yangshi Chen pointed out that I had done something kind of stupid. Get rid of this, okay? Wait, maybe I shouldn't have gotten rid of that. I'll keep that going. Okay, and notice that we are using audio now, and I had not connected the audio output of RTCMix to the Easy DAC, which will turn it into sound that we can hear, okay? So let me see this now. Hopefully this will now work. Okay, let's try it out. Yes, but it's only working on my computer because I now have this misset. Okay, audio status. Right, we want to go to the external headphones. Yes. Okay, life is good. Okay. Right now, let me take this and increase it. There we go. And now are you ready? Chaos! Oh, I love that part. That's the end. Okay. All right. Woo! Fun. Okay. Now, a couple things I want to point out about this before we leave it, and we're going to go on to another tractor. Okay. First of all, this isn't actually quite correct. Okay. What we really want to do is only iterate when we receive a new R value, and then we'll just spin the X's out of that, okay? By assigning a new random value to X each time, it will work, but it's not the actual, like, legitimate sort of full attractor, okay? Because essentially I'm just, recomputing everything every single time, and the idea is that it builds on itself, okay? Again, it works. I'm happy. The other thing is, you notice that I was using wavetable, it had like a weird ringiness to it. That's because it's being generated very quickly, and it's being generated at a relatively small time, 0.1, okay? So they're only 1/10 of a second long, these little wavetable things that I'm making, all right? Now, it turns out that back in the olden days, when computers were slow, we used to do things like calculate envelopes at a much slower rate than the audio rate, because it was expensive, computers were slow, doesn't matter anymore, but it still retains the default. It only calculates audio the amplitude envelope 1,000 times a second, not 44,100 times a second. And when you have very tiny notes, you don't have enough of those sort of values to make it work well, and you get distortion in the waveform. All you have to do is say reset 44,100, and that will guarantee that it will calculate it at the audio rate. In fact, I just do this. We're in the process of rethinking like a new release of RTC Mix, and this is one of the things we'll probably change because computers are extremely fast now, and I have never had a problem with using the reset value like this. Maybe in some sophisticated Unity where you got a lot of stuff going on, you might run into some problems, but probably not. Okay, so now if I do that, you'll hear it sounds a little bit more clear, like a clearer wavetable. Yeah, there it is. Oops. Ooh, I went into infinity, yeah. Okay, so why didn't it crash when I went up here? Because of this. This is clamping it between 0 and 3.99. So I got lucky, because if that wasn't there and I was using the values directly, it would have crashed. Because computers don't do well with infinity, sadly. Okay, so that's that, okay? Now, I want to move on to another cool attractor, and I'm going to bring up a web page here for this one. And this one is different because the equation is different, and it requires a different kind of interpretation. I'm also going to try and show you different ways of interpreting these things. You know, it's always easy to just say, oh, let's map it to pitch and do something cool like that. In fact, let me do one thing here before we leave. Let's see, I think I have this pre-made. So let me go here and see if it is. Let me get rid of this nonsense. How do I get rid of this nonsense? I guess I don't need to get rid of that nonsense because I'm not going to. Okay. Let's suppose that rather than just multiplying x by 0 to 1,000, I want to put it in a specific range. Essentially, I want to do this, but I want to do it inside RTC Mix. How do I do that? Well, I create a function. You can build a function in RTC Mix. And this function is called mapIt. And it's the same arguments that you give to that scale object. You give it the value that you're checking, the input low, the input high, the output low, and the output high. And that's the equation. You don't have to worry about it because it's already there. That's the equation you use to calculate that. So down here, okay, so instead of frequency being like just x times 1,000, I'm saying take x, and x is going to be coming in between 0 and 1. And let's say make it between only 300, and we'll say 300 and 400 hertz coming out. Okay, so this will clamp down on our range of stuff. Okay, let me put this up at like 2.9. Start this out. Oh, I don't have that reset line there, and I don't have the print off there either. So you're going to hear it kind of annoying. Okay, but now if I do this, notice it's chaotic, but it's in a much more restricted band. Okay. Okay, so that operation is called mapping. We're going to use a lot in a lot of different contexts. Okay, so we're probably going to use that function. There's one other thing I was going to show you, but I'm going to hold off on that. Okay, let's go ahead and look at this other attractor now. And I'm going to have to, unfortunately, let's see now. Okay. Yeah. How do I get rid of this?
The Zoom band at the top is annoying.
Yes, it is. It's in the way, and I can't get it. Oh, boom. All right. Okay. Let's go to my handy thing here, and we will bring this down so I can actually type into it, okay? CMC, okay, Sites Music Columbia EDU CMC courses, okay. Sites Music Columbia EDU slash, see, I was supposed to like set this up ahead of time and I forgot to. Right, okay. That's Sound Advanced Topics 1 from G6610. We want to go to fall 2003. And we're going to go to week 2. All right. Yeah. Okay, I'll have these links in here. This is basically when I first taught this class back in 2003. There's the equation that we've come to know and love, r times x times 1 minus x. There's the graph. And back then I wasn't using Max MSP, I was using another thing which allowed me to easily do these cool colors. So yeah, cool. All right. And down here now is this thing called the Lorentz attractor, okay? And that's why it looks like this. Now, why are these things called attractors? That's because if you iterate these equations, the outputs will lie along one of these lines. Basically, the line is attracting the output somehow, okay? This is what the Lorentz equation looks like, okay? It's actually a series of 3 operations, and you can see they're very simple, but it's different because it's not producing a single x value. It's producing 3 weird values, and these values, these are actually the results of creating differential equations. These are showing you not the actual value, but how much the x value is going to change for each time you iterate it, how much the y value is going to change for each time, how much the z value. So what we're going to do is we're going to set up with an initial x, y, and z, and then we're going to run this equation and add those values to it. So x, y, and z will get new values, and they'll gradually kind of change. And if we're lucky, they'll plot this thing out, okay? So let's take a look. And again, I'm not going to spend the time coding this one up because, yeah, it takes me a long time to code things up sometimes. And I'll use my previously made thing here. Let's go back to this. How are you guys holding up? Is this getting too boring or slow or anything like that? Okay, well, let's look at it, all right? Here we go. There's my values. Now, I'm also initializing it a little bit different. You know, remember, I can't put those values in here because every time it came through, remember, we're going to be adding numbers to those values. And if I reset them to 1 all the time, it'll just be 1 all the time, okay? So I'm initially setting them by just hitting this, and this is a text edit box, and it'll just send that text into RTC Mix, and it'll go, oh, okay, I'm going to say x is 1, y is 1, and z is 1. What do I do then? Well, here's my delta. This is how much in time we're going to like shift, okay? And then I calculate the Lorentz equation here, okay? Then I say, well, the new x value is the old x value plus delta times this thing that I calculated, okay? So that's the heart of doing the Lorentz calculation, okay? And again, I don't want to go into great detail here because you can look at it later. Again, oh, I forgot to show you, I'll do that later, where you can find all this good stuff on the web, okay? And then I flip the x new, y new, and z new values that we calculated, make them the old x values so that when they come back in, they'll do all this stuff over here. And then we do the whole thing all over again, okay? It's easier to see it than to kind of try and wrap your head around it now. So we'll do this, okay? Initialize this, and then bam, watch what happens to these values. This is x, y, and z. Every time we hit a bang, they're going to change slightly. Okay, and if you watch them, they're going up 2.6. Look at the y value, 2.9, 3.3, 3.7, 4.2, 4.7, 5.6. So even though they look kind of random, they're actually going in a progression, okay? And we can actually see that progression if we plot it. So let me put up the next one, which has a nice plot of the Lorentz attractor. Let me put up the next one, which has a nice plot of the Lorentz attractor. There we go. All right. Okay, now, here's what's weird about this Lorentz attractor. Oh, damn it. Give me a break here. Oh, I forgot we're recording this. No, Mom, I didn't mean it. Okay. Don't use those bad words, Brad. Okay, now, I'm doing something a little weird here. Notice that I don't have that bang with the x equals 1, y equals 1, and z equals 1. Instead, I have these things go script 0 and go script 1. Okay, remember, this is also a way to teach you a bit more about the RTC mix thing. Well, what you don't know is that this object, the RTC mix tilde, can have up to 20 different scores. Here we're calling them scripts on it. And we can trigger them with these messages. Let's open script 0 and see what it says. Well, look, it just says initialize the values. Okay, so it's the same thing that we were doing before. Okay, I'm showing you this because in the future we're going to run into situations where the initialization is much more complicated, and we want to segregate that into like a separate script. Okay, and script 1 is then simply the thing. However, I've included my mapIt function because now I'm going to map the values that I'm going to plot from here, here, and here. And this was from actually running the Lorentz attractor a bunch of times and looking at the values. I discovered that x goes from minus 25 to 25, y goes from minus 30 to 30, and z goes from 0 to 55. Okay, so it's not the nice 0 to 1 that we had with the logistic map. Okay, so that's going to basically map that to our square width here, which is 200 pixels. So that's where you're seeing those 0 to 200 and all that. Okay, and we're going to put out. Now, we also have 3 variables. This is only a 2-dimensional plot, so I'm just going to choose 2 of them. I'm going to plot x against y. But we could then plot x against z. You know, ideally, we'd have a 3-dimensional modeling program, and we could see the whole 3 dimensions of the Lorentz attractor, which is pretty cool, you know, but we don't. And that's way beyond the scope of this class to build one right now. When we get to Unity, maybe, because it's already 3D, all right? So now we can actually turn this on, and I'll initialize it by saying go script 0, bang. And now when I turn on the metronome, it will start calculating the attractor, and you'll see what it looks like, x plotted against y. Boom. Okay. Cool, huh? Okay. Now, just for fun, we can go in here and let's say, well, let's suppose that we wanted to plot x against z. Okay. We can say zval and zval. This, by the way, this is the reason there's a +2 here. That's to give the little point a little bit of width, because otherwise it would be too tiny for us to see on the screen. Okay. That's just a little plotty thing. Okay. So now let's initialize it again. Clear this off. And now this is x plotted against z. You see it's very similar in certain respects. Okay. All right. Okay. So we plotted it. Now we're going to sonify it. Okay. But we're going to use a very different RTC mix instrument for this one. Wait, let me make sure I'm not leaving anything out here. Print out the values, showed you the early class, plot scaling, yeah. Okay, next message, right, scale mapping, right. Okay. You have 3 variables, all right? Now, usually with the RTC mix instruments we've just been using pitch, right? So we go, well, what else can we affect? Amplitude? Well, it'll be soft and loud. That's not really cool. Pitch, amplitude? No, it'll be soft and loud. There is an instrument that's widely used in computer music that actually has 3 salient sort of parameters that you can use that will affect the sound greatly, okay? Let me bring this one up. Let me bring this one up. And I'll show you this cool instrument. Oops. Yeah, now notice in my initialization, I just did this inadvertently. I put my amp calculation, my amp and my wave calculation in there, okay? But I'm going to open script 1. Okay, so here's all our Lorentz stuff. Oh, and what's this nonsense here? FMinst, okay? This is a synthesis technique called frequency modulation, okay? And basically, the sound you hear is determined by this carrier frequency and the modulator frequency and a thing called the FM index, okay? It turns out that the carrier frequency plus or minus n times the modulator frequency, and n is the carrier index. Well, what does that mean to humans? Well, there's an easy way for you to find out, because if you go in and unlock your patch and hit Option or Control on Windows machines, Option RT-CMix, it'll bring up the help patch, which I think I showed you last time. Did I? Good for me. Okay. All right. And it's hidden away, but over here in dynamic params, it's actually showing off something that we're going to talk about probably next time, that allows you to fix the frequency of something, a parameter dynamically. But this is an FM example, okay? And it also has a filter. I'm just going to turn the filter up so we don't hear it, because we're not interested in that. But we're going to hear FM. Okay. Now, let me turn the amplitude down a little bit. Now, if I modify the carrier frequency, it does this. Oh, I need to. And if I modify the modulator frequency, it does this. And if I modulate the index, it does this. So we've got three parameters there that greatly affect the sound. Well, it's just made for the Lorenz attractor, right? Okay. So we're going to use an FM instrument to then sonify that Lorenz trajectory. Okay, let me get rid of this nonsense. How are we going to do it? Let's take a look real quick. We're simply going to map this down here to between. This is done by kind of knowing what to do. Here's your ranges of the initial parameters coming in. We're going to say, make the carrier frequency be between 100 hertz and 1,000 hertz. Make the modulator frequency be between 100 hertz and 1,000 hertz. And the FM index, which is like how many of these harmonics are there. Again, I'm going to put in some links to like FM theory if you're really that interested in it. It's widely used. A lot of synthesizers. The ever popular Yamaha DX7 was built on this thing. I got a story to tell about that in a second, okay? Actually, I'll tell you the story now. This patent, this instrument, FM, this technique was developed by John Chowning at Bell Labs when he was working there in the late 1960s. John Chowning, if you don't know, is one of the founding fathers of computer music. Fathers, yeah, sorry. That's the way things were. That's okay. That's a different discussion. Okay. But John's a really nice guy, and he founded the Stanford Computer Music Center. All right. And while he was at Bell Labs on a sabbatical, he sort of developed this weird thing called FM. So, I'm getting a lot of cool sounds out of it, And bear in mind, to get cool sounds took like a week of calculation. So it was easy. You had three parameters. It was very efficient, very fast. So the Bell Labs people said, by golly, John, that's a really snazzy thing. Why don't you just patent it? So he said, all right, I'll patent it. So he did. Okay, fast forward to like 1982. And Yamaha Corporation had been developing very fast VLSI, they called them, chips that could actually do FM in real time. Now that was a big new thing for computers. All right. They said, Mr. Chowning, we would like to use your FM patent. And he said, sure, make it so that the software is free for people to use in universities like us. And you can, give me 10% of your royalties and give Stanford 3%. That was kind of a standard thing back then. So the Yamaha folks said, sure. And they created this synthesizer called the DX7. Revolutionized the music business. How revolutionary was it? Well, between 1985 and I think 1987, the royalties from that 3% patent that Stanford got was the second largest money earner for Stanford University. This is a really big deal. The first one was like from Genentech. It was a gene splicing thing or something like that. So yeah, John retired. Stanford has lots and lots of money, or they used to. Yeah, you've all heard this. If I had my normal presentation up, I'd play this for you. But Taco Bell commercials, when the Taco Bell hits, that is classic FM sound. Okay. And it was on the DX7 too. So anyhow, we're going to use that because we can use it for free. Actually, the patent's expired now, I think, so we can use it for free anyhow. But let's go ahead and plot it out, okay? We'll initialize it here. And this time we're going to hear the trajectory of this thing, okay? Okay, you get the idea. All right, cool, huh? All right, so how am I doing on time? Oh, good, I'm doing okay. I'm going to bring up one more patch because it shows both, all three variables are being, oh no, this is not. What is this one? Oh, this is a fast version of the FM. No, it's the wrong one. Hold on, guys. Oh, yeah. Yeah. I want to show you the Lorenz attractor. So, of course, I start with the population attractor. Yeah, Lorenz 4. That's the one I want. Yeah, we're going to see X against Z and Y against Z in this, okay? And let me make it a little bit faster because I want to point out something that's really scary about this particular attractor, okay? And let's go down here and let's make our FM instrument be a little bit smaller in terms of, oh, this is modal bar. No, this is actually cool. This is a marimba sound, okay? So it's going to get, instead of like the FM frequency, it's going to get amp and frequency and hardness, okay? These are the three parameters that we're going to give to it, okay? So let's go here and start this up. And we've got the old way of initializing it. Uh-oh, something happened there.
Because of the zero.
What's that?
If you go to the RTC mix thing.
Oh, did I write something else wrong?
It's 0 point. There's nothing
right.
there.
Start. That's what it's supposed to be. Sorry about that, guys. Okay, here we go. Let's start this again. Initialize. Maybe that's a little too fast. Okay. Yeah. Let's go back to 100. Yeah, 50 might be good. Okay. There's something I want you to see. Okay. Well, you've seen it already, but I want to explain what it is. Okay. Cancel. I want to say save. All right. Clear. Lock it. Clear. Turn on. Do this. Oh, clear this one. All right, here we go. Okay, now, watch what happens, okay? It's going to hang out here for a while. Okay, you know what's going to happen, right? And it's going to hang out here for a while. It's going to hang out here for a while. We're going to watch it hang out there for a while. But then something changes and it gets a little bit out of control, and then it goes over to there. And it hangs out there. Edward Lorenz, who developed this attractor back in the early 1960s, was a climate scientist. What you're seeing is what climate change could do. Everybody thinks it's going to be this gradual process. Well, here we are, we're living in kind of happy climate here. It's getting a little bit warm in the summers and cold in the winters, but all of a sudden you're going to cross a threshold. And according to his models, we will go into a completely different climate regime, which could be really, really bad for humanity. This frightens me because it's a model and it works, you know, and to be able to see it like this and to hear what happens, especially with the FM stuff where it kind of goes like that, you know. So, yeah.
What kind of climate regime would be?
Literally chaos.
Yeah, I don't know. I didn't read that far. Well, first of all, his papers are really dense, you know.
Yeah.
It's probably a climate regime where there's like 100 millibars of something at somewhere, you know. Yeah, but it's not necessarily going to be a good one. I mean, yeah. Okay, lesson for the day. All right, one more attractor, and then we're going to do some fractal stuff. All right, this one I'm not even going to bother to code. I'm just going to show you the attractor and talk about the problem that we have in sonifying it, okay? It's this thing called the Hanon attractor, okay? And there's the equations for it down here, okay? And you'll get out an X and a Y, and we're actually plotting X and Y here. And this one, when you see it sort of happen, which you're going to see in a minute, you see why it's called an attractor, because what happens is it doesn't make a trajectory here. A lot of these attractors will just plot these points randomly, and gradually you will see that this sort of figure is emerging from them, okay? And again, that's why it's an attractor. The problem is, if we're going to sonify this, if we do what we've been doing, where we like just take the particular parameters of a single point and then map that onto a sound producing thing, it's just going to sound like chaos. It'll go so beep, 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 because it's going to plot a point here, then it's going to plot a point here, then it's going to plot a point here, then it's going to plot a point here. So the trick is to how do you capture that parameter shape and also the evolution of the attractor? And my solution for that is this thing called the Hanon3.maxpatch. And again, I'm not going to show you. I had to use some JavaScript in order to make this happen because it was a little bit complicated. But I'm just going to show you how it runs, okay? Come on. All right. So what I'm going to do is I'm going to run, and I have a little slider here that shows you where it is. I'm going to basically iterate along the path of where that attractor is going to appear. And I'm going to plot points by the attractor. And again, you know, this is the JavaScript code if you want to look at it. Okay. And there is the actual code for doing the attractor down here. No, that's the code for keeping track of it. Well, we're not going to look at that code. All right. You'll have it online. You can see it. Okay. And this is, we're using RTCMix simply to create the sound now. It's just going to get values and it's going to play them. All right. But what's going to happen is because of this JavaScript, it's going to run it like this. Okay. Let's hit init. Let's turn this on. So it's kind of like weird, chaotic Steve Reich, you know, or Philip Glass more likely. And you can see that the attractor is now beginning to take shape here. Okay. Okay. You get the idea. All right. Fun. So again, that's a different way of thinking about how are you going to approach sonifying that particular attractor, you know, because it's being plotted not in a Lorentz or population equation kind of way. Well, the population equation is, you know, for any given value of R, it's doing that, you know, but we can change R. This one is just the attractor is fixed and it just fills out with these weird things. And again, these look like relatively benign equations. It has to do with the fact that you're taking the y's and the x's and you're putting them back in and then running it over and over and over again. That makes a difference, okay? All right, before we leave attractors, I want to show you one place that's really, really cool. You know, it's like, wow, Brad, how did you get all the code for these attractors and figure them out? Well, it's because I'm a genius of computer music. No. We recording this? No. Yangshi is. Yangshi is, okay. We're going to go to this guy named Paul Bork. There it is. Okay, this is a guy that's working in some university, or is probably retired by now, in Australia somewhere, okay? And he's got all these are all links, okay? And let's look at this one that says fractals, chaos, and self-similarity, okay? What he has is a whole bunch of stuff, okay? There's the Rossler attractor. Ooh, let's take a look at that, okay? So if you click on this, he gives you the equations for them. So you don't have to go and like figure it out. And he'll also even give you some example code for running the attractor. And you can see all the cool things that it does like this. And more importantly, he gives you those values that you need to have for the equation to work properly. Like here's a value A, there's a value B, there's a value C. Look, he tells you what they are. Because if you don't have those coefficients, you can't run the attractor, or you can, but it's going to do something like go to efficient. Let's see, this Buali attractor, what does that look like? I never saw that one before. Oh, looks fairly recent. Yay, good for Paul Bork. Look at that. Oh, look at that. Oh, where's the equation though? Oh no. No equation for that one. He must be getting old and lazy like me. Let's look at the VR attractor. What does that look like? Oh, that's pretty cool. Oh, no equations. Well, this isn't working out as well as I thought. Let's look at Clifford. Equations, yay. And look, that one's really simple. It's really simple. Look what it does. Really weird stuff, okay? So these are kind of fun. I have a class, and I'll link it in, where we actually went through the process of translating that into sort of code that we could run with RTC Mix. So it's kind of fun. You can hear what these guys sound like. What's happened
We
here?
hear these with this setup that we had.
What's that?
For the other attractors.
Yeah.
We hear if you use these codes.
Yes, you could. Very
Very
much. You easily could.
Those max patches then.
Exactly,
Alright.
exactly. Guys, my computer has stopped working. I mean, seriously stopped working. I can't even bring up the, What am I gonna do now? I wonder if it's still recording. Boy, this is turning into a fun class.
Maybe call Timothy.
What's that?
Tim, is he still on?
Hey, Tim, can you hear me? Are you still there? He may not be there.
I can hear you. Your video, it's working, yeah.
It is. How weird.
Yeah.
Okay. I'm going
See
to
your, see your mouse moving.
have to somehow shut this down. Huh. And I'm going to have to restart it. Dang. Yeah, this is like, well,
Do keyboard commands work? Oh,
that's working. Why isn't, oh, good. Whew, yay. I don't know what happened. That was scary. No, it wasn't. Come on. Computers crash. That's just what happens to them, okay? All right, so I've shown you that. All right, now we're going to enter a different world for the remainder of the class. I want to show you, remember when I talked about this iteration as being, I called it a little bit recursive, where you're putting the values back in? Well, this next thing that we're going to talk about, fractals, is basically built around this process of recursion, okay? Well, what do I mean by that? Well, let me show you some things here. Okay, let me get my, not that, let me get my, get this back over here. Okay, I'm going to, let's see, go to fall 2015. Wait a minute. Hold on, guys. Yeah, okay, right. Okay, sites.music.columbia.edu / sorry, I should have had this done ahead of time, cmc/courses /G6610, okay? /Brad /week5. Okay, good. All right, this was an early class, okay? None of these work anymore. I'm going to show you a different page with a bunch of cool stuff on it, okay? Basically, fractals are a way, this guy, mathematician named Benoit Mandelbrot. Have you all heard of the Mandelbrot set? Okay, all right, we're going to show you that later too. He was investigating the incidence of errors on IBM computers at the Watson Research Center, and noticed that there was like this weird patterning where they clustered together. And based on that, he came up with this idea of fractional dimensions between something. And his thing is like, you know, how long is the coastline of Britain? Well, how long it is depends on how large your measuring stick is. Because if you get it smaller, you start getting all the nooks and crannies of the coastline. And that's essentially what fractals are, okay? So this was actually back in the early 2000s, this was really impressive. That was a picture generated using fractal techniques, okay? So all the mountains and everything are fractals, okay? And this is the basic way you do it. This is a thing called the Koch snowflake, after a mathematician, George Koch, who kind of developed this thing. You basically take a single shape And then for each thing, you do this recursion where you come back around and you put in the shape for every straight line, and you get a shape like that. Then you can recurse again and put in that same shape for every straight line, and you wind up with this very wiggly, again, we're using smaller sort of measuring things like the coastline of Britain. So all of a sudden, you can get very complicated shapes out of this very simple technique of just applying something again and again and again at smaller and smaller scales. So I thought, well, that's pretty cool. And, you know, I like those mountains and everything like that, you know. But let me go down here and see where I am. Yeah, let me stop there. And well, I'll show you the application that I did in a second, but I'm going to show you some other stuff that's fun too, okay? And basically, there's a lot of examples online of fractals and things like that. And let's see, sites.music. Columbia.edu CMC/courses/G610 fall 2015. Okay, and we're going to go to week 6, I believe. Yes. All right. So I'll link these into our current class too. But this is kind of fun, all right? This is what's called a fractal microscope. Now, it's going to show you this thing called the Mandelbrot set that was named after Benoit Mandelbrot. And what the set is you look at, it's a little bit complicated. You iterate values called complex numbers. And if you remember this from like high school math or something, complex or, you know, current math, complex numbers have a real part and an imaginary part. Okay, it's a way of representing two-dimensional quantities and doing all kinds of calculations. They use it in filter design and digital signal processing a lot. But the Mandelbrot set is defined by you basically square the complex number, and you get a new complex number as a result. If that complex number goes to infinity, it's outside the set. If it stays not to infinity, it's inside the set. Turns out that that simple decision makes an incredibly insane thing, okay? That's what it makes, the Mandelbrot set, okay? And let's not use grayscale, let's use like blue because it looks a lot cooler that way. And what I can do is actually zoom in and look, there's actually little Mandelbrot sets inside the Mandelbrot set. And I can actually zoom in on that and look. That's the boundary between points that go to infinity or points that stay inside the set. Look at this one. It's taking it a lot longer. Now, think about how many times I've just gone in and how complicated this thing still looks. This is really insane. So people were just fascinated by this, and they're thinking, oh, we're going to do all kinds of stuff with it, you know, and especially make some music with it. Like I said, I'm going to put this up on the class website. Let's see, let me get out of here. Yeah. There's other ones here, another fractal microscope. There's other things here. If we have time tonight, we probably won't. I'm actually got some pieces here that I'd like to play for you that were created using these fractal techniques. All right. L systems we may not get to. We'll talk about them next time. And I also want to show you how to deal with sound files next time. Like I said, next class is not going to be this intense. Okay. So yeah, I'm trying to keep it nice for everybody. I hope it's nice. All right, because I like you all. Let me give you an example of one of the cooler interpretations of the Mandelbrot set that I've seen. This is done by a friend of mine named Nick Didkovsky. He teaches at NYU occasionally. He's taught us here when I've been on sabbatical in the past. But he's actually a high-end kind of graphics guy that works for, I think, Rockefeller University. And he's done some visualizations of molecules that have been on the cover of Nature and Science magazine, which is a really, really big deal if you're working in the sciences. But yeah, what he did was he said, you know, a lot of people take the Mandelbrot set and they just use it statically. You know, I would like to actually capture the process of deciding if a point is inside or outside the Mandelbrot set. So he came up with this thing, okay? It's called Mandel Music. And a bunch of his students came up with ways of kind of sonifying what you're hearing. But if you click here, it'll start a point and it'll start that process of deciding if the point is inside the set or not. So if I click here, that's in the set. I think that's in the set, but look, that one's outside the set. Okay, let's do another person. Okay, let's try this Steve Ward. What does he sound like? Okay, let's make him outside the set and see what happens. Yeah, not much. Okay, let's clear this. Let's try, say, Kyogi Lee, and let's try Kyogi outside the set. Yeah, not long. Let's try him right. No, 1 to infinity. So you can actually hear what's happening. Some of you might recognize that sound. That's FM. And he would actually do concerts where he would play this as an instrument. That's not such a good, anyhow. So yeah, I always like showing this because I think it's a really interesting way of thinking about sonifying something and using that Mandelbrot set too, okay? But what I did was different, actually quite a bit different. Let me bring up our little thing here. Yeah, here we go. I'll leave this here because I may want to access that page again. Okay. When I was a kid, I used to go fishing with my father at the end of the summer up in Canada, at the Manitoba-Ontario border. And where we camped, there was this big sort of cliff across from us. And like one night I got like gunk on my shoe. So I went down to the boat and I was like whapping the shoe to get the gunk off. I go whap, and then it would hit that cliff and come back and go whap. So for like the next 10 minutes, I'm down there whipping my toe. What in God's name are you doing, Brad? Listening, Dad. So I thought, wow, when I started learning about fractals, I thought, well, I could model that cliff face as a fractal, like that, okay? And when I make a sound, it will hit that fractal boundary and bounce back with fractal delays. So what I did was I took and basically made a fractal that laid itself out in time here, and I made each one of those be a delay from the point source that's going to be over here, okay? So that's essentially what's happening, all right? Let's look at the RTCMix code for this, and yeah, we'll see. Maybe I'll take some time and just play a few pieces after that. Let's go here, all right? So here we go. Fractal A1, okay? Now, I should mention there's a stupid way to do what I'm talking about, and there's a more intelligent way. Excuse me. This is the stupid way, all right? Well, basically, this is not the stupid way. This is just showing you the delay instrument. It's called del1, all right? And it gives it a start time on the output, a start time on the input. In this case, we're going to process it live, so they're both 0. All right. How long do you want it to run? Just run forever. What's the amplitude that you're going to use? Now, here's where I want to make a differentiation between signal processing instruments and synthesis instruments. With synthesis instruments who are using amplitudes like 10,000 and 20,000 because of the 32768, we're changing that, by the way. Since this is processing audio coming in, it already has an amplitude. So the amplitude argument here is just a multiplier of what's coming into it. So if we want it to be the same loudness as coming in and going out, we just say a multiplier of 1, okay? Then there's the left and right. 0 is left, 1 is right, and then 1 is the ring down duration. Yeah, that's ancient, just put 1 there, all right? And notice that I'm only coming out of the right signal thing here. That's because the del1 instrument will take its input and it will put the original signal in the left and then the delayed one in the right. That's to get that nice kind of ba-doop, 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 ba-doop sound that you hear sometimes on like rock stuff and things like that. We just want to hear the delay, so I'm only going to use this right output. So now we can, hey, look, there I am, and now, hey, there's my delay. Ooh, gets a little loud. All right, so now turning that into a fractal delay. All right, here's what we're going to do. Shoot. Oh, they can see. All right, I'm going to write on the whiteboard here. What we're going to do is we're going to take a span of time, okay? Let's say between 0 and 1 second. And then we're going to create a thing called the divisor, okay? And let's say we're going to make it be 0.7, okay? So we'll generate a delay point there, okay? And we'll generate a delay point there. Now we're going to take this and this span, we're going to divide that by 0.07 and make whatever that's going to be, what's 0.49. And then we're going to take this one, which is a span of 0.3, times that by 0.7, which is going to be 0.21 plus 0.7. It'll be somewhere in here, 9.9 something. Okay. Then we can go further. This is called recursion. Just like with the attractor stuff. We're basically doing what we did with that little weird snowflakey thing that I showed you. We're just taking the same delay and applying it over and over to this thing. Now, the stupid way to do it is this way, where I go through myself and I calculate out all the different delays based on this division thing and, you know, where it's going to start and where it's going to stop and things like that, okay? And, you know, I had to type it all out, and you've seen how good my typing skills are. But in fact, it does work. I'm going to turn it down a little bit. Oh, I noticed that this does nothing, probably because of Zoom, but this does. So I'm going to turn it down there, okay? Hey. All right, now you hear, hey. There it is. Turn it up a little bit more. Hey. Okay, so it is working, but like I said, that's a stupid way to do it. Let me show you the more intelligent way. All right. And that is, we're going to define a function called make delays. All right. Now this is where this is fun to think about. I really love thinking about this. There's a computer language that I use for my dissertation I'm going to talk about in a couple of weeks called Lisp, which is kind of built on recursion. And this recursion is amazing, okay? What you do with this function is you're going to give it the delay time in, the amplitude in, because those are going to be calculated, and then the level that you're going in, okay? So, first thing I do in this function is I say, all right, I have a delay time in an amp. Let's go ahead and create the delay. So there's the delay here. Then what do we do? Well, we have this thing called number of levels, or how far down are we going to go in this process of dividing things up? And I'm setting the levels to be 3. So if the level that it's currently at, that was passed in here, is less than the number of levels, here's what you do. You call the make delays function again with the delay line in modified by that division thing, which is 0.3, and the amp in modified by that division thing. And then you call it again. Remember, I had to do like 2 different lobes for each one, all right? So what you're doing is you're recursively calling the function. The function is calling itself again and modifying what it's going to give to the next version of make delays down. Now look what happens here. This turns into 2. Each one of those turns into 2, so you get 4. Boom, boom, boom. Each one of those turns into 2, so you get 8. You know, this is how you can generate a whole host of delays very simply. Yes.
This is probably a silly question.
No, it's not.
How? Because I've definitely like worked in Chuck or something, and like if you or I and it just won't work if like the function is in the function, or so how is this one allowing that?
Because we're good programmers. Take that, Perry Cook. No, you have to, Doug Scott did this, and you have to be very clever about how you index what you're doing in what's called the parser, and yeah, it's a very powerful tool to have in your tool set. We didn't have it in the original RTC mix, this was added a while ago, but yeah, and you have to be careful, I mean, if I set the number of levels to even like 4 or 5, it will overwhelm the computer at some point, because think about it, it's doing an exponential increase. It's like the famous thing where, the emperor said, give me a grain of salt on like each chess piece, and like it's more than protons in the universe, well, we can make more delays than protons in the universe if we want. Yeah, it's most computer languages will have this. JavaScript, for example, C and C++, of course. But if you're creating a specialized language, you don't necessarily need it, okay? And Chuck, I don't think is considered a full programming language. Well, it is, yeah, it is. We've had a lot of arguments about Chuck and RTC. All right, so, and then I call it at the end to get the final delay, all right? So let's hear what this sounds like. This is with 3 levels. Okay, and yeah, I think I've got the thing, so I triggered it off here. Hey. Oops, still a little bit too loud. Don't worry, I'm watching it, Anna. Okay. Hey, there's a lot of delays. Yeah, I can pound my foot. Ooh. Okay, so all of a sudden you can get very complicated things happening with very simple sort of like scripts. And yeah, that makes me happy. Okay, there was one other thing I was going to talk about, and I'll see how important it is for next time. Let's see, it wasn't this one. Oh yeah, I saved this one for a reason. Okay, it's kind of a variant on fractals called L systems or Lindenmeyer systems. And they were developed by a Belgian guy named Aristide Lindenmeyer, and it's a way of modeling growth. And you can kind of see when I say it's a fractal, what it does is instead of like, generating delays, it generates branch points. So you have 2 branch points, they're going to turn into 4 branch points, going to turn into 8 branch points, things like that. And you can get these by determining, these sort of ways of dealing with how the branch points are going to be put on. You can get very complicated figures. This is by the way a very famous fractal called the Sierpinski triangle, and so it's showing that the L systems are basically fractals. Okay, they've been used a lot in music, in particular. This Luc Dubois did his dissertation using L systems, okay? And let's see, it's down here. Projects, there it is, dissertation. So he basically came up with this whole system for generating music using L systems. And you can actually hear. You can see how it's kind of filling out the branch points. Okay. If we take it along to here, it'll be a bit filled out more. And play. So basically all these different things, this is a piece he did for string quartet, and the graphics were generated by L systems. And then there's that was for flute, sorry, solo flute. These are the string quartet pieces. And if you're interested in this, like I said, maybe I'll show you a few more next time before we get into some of the other stuff next time. His dissertation is actually quite readable, and it talks a lot about how you set up these systems and how you can think about interpreting them. It's pretty nice. Okay, but let me do this. Like I said, fractals kind of captured a lot of people's imaginations, and that's not the one I want. It's back here, yeah. Let me play you, I won't play the whole thing, but I'm going to play you a couple of pieces when fractals kind of were really ascendant in the world of music. How many of you have heard of Charles Dodge? Okay, he's kind of a fairly well-known original computer music guy. He's about the same age as Paul Lansky, for example. And Charles actually worked here at Columbia back in the olden days, but then he left to found the studios at Brooklyn College. That's where Curtis Bond was his assistant director. Some of you may have heard of Curtis. And Charles eventually retired teaching up at Dartmouth. And he did a pretty well-known piece based on sonifying the Earth's magnetic field. The piece is called Earth's Magnetic Field. And he also wrote one of the earliest books on computer music that was kind of a standard text for a long time. But this is an example of a piece that Curtis helped him quite a bit, but this piece was completely generated using a single fractal technique. So they just kind of let it go. And this is what came out. I won't play the whole thing. It's so nicely peaceful. You know, I was thinking maybe I should just let the whole thing play. We actually do have enough time, but it's kind of weird. Playing music in classes is just a weird thing to do, you know. I mean, because you're just sitting there going, you know. But yeah, and you can really hear how the fractals are kind of unfolding, you know. And it's a very elegant piece. I'll play you one other one. This is this guy, Michael Gogans. He's still active here in the city. He's done a lot of work for a language called C Sound. In fact, he wrote the web version of it. And he was also famous. He wrote a very dense but very useful paper in the Computer Music Journal back in the 1990s called Iterated Function Systems. And it's a way of designing chaotic attractors to create particular results. In fact, this is how the JPEG algorithm works, if I'm not misunderstanding it. That you can basically, when you choose like how high resolution you want in a JPEG image, you're choosing how much to iterate to create that image. But it does it by dividing it up into little tiny things like that. David, do you know if that's true or not? I might be making that up.
Sounds right. I believe it, but I don't know anything.
Yeah. Anyhow, but so he created a whole bunch. All his music is done using these fractal, chaotic L systems or whatever techniques. His approach to composition, he says that he wants to, like with the Mandelbrot set, when you're like going in, he said he just wants to find a rich area that he can kind of just go into and having it just generate the pieces for him automatically. Sounds kind of like contemporary AI, huh? Ooh, it all comes together. I do want to show you one thing about AI, okay, before we go. But I'll play you a little bit of this one, okay? suppose here it is. And I'll link some of these in for you to listen to also. I am shutting it down a little bit early because I forgot to tell you a couple of things, okay? And one thing we're going to have to like kind of deal with next time because this is something that's important to know. How do I get audio to come into RTC Mix? Well, it's pretty obvious when you look at the script, that thing right there. Okay. Now here's the cool part. You can also put in a sound file name there, and that will come in instead of the audio. And then all of a sudden, things like the input skip and output skip make sense because you can skip into an input sound file, like maybe 5 seconds before you get to the part that you want to play or something like that. Okay, so we're going to be talking about this and about another way of setting that up next time. Okay. And the last thing that I wanted to say is let's go back to the main class website, okay? And I'm going to go ahead and kind of give you this assignment ahead of time, okay? Because it's going to come up before we know it. Let's go to syllabus. Okay, so here we are, all right? And then next time we're going to talk about, I just made that up. I have no idea what I meant by that. But we're just going to finish off some of the RTC Mix stuff that I wanted to make sure to cover. Okay, and then we're going to jump into AI, all right? And this one, yeah, I've got some stuff in. This one I want to talk about because maybe you want to start working on it a little bit now. Those 3 weeks are going to be kind of weird because I don't know what we're going to talk about really. You know, I know a few things. Yangshi is going to be talking about some stuff too, but this class in particular is going to be completely free form because, you know, we've all heard of some of the, you know, uses of AI for music, but it's changing radically and there's so much going on. I don't even pretend to know half of it. So your assignment is to maybe find some cool or interesting examples of using AI in music and bring in web links or whatever. And we're just going to discuss them, you know, and figure out what's going on there, okay? And oh, I have to put in the special guest. That's actually set, that's going to be Lara Lewison. She's a former student here, and she's gone on to do really interesting things with both AI and Unity. Yeah, so you'll hear more about her later. Okay, so yeah, think about that, and let me shut down the recording. Hopefully that recorded okay. Let me go to Zoom. Timothy, I think we're going to turn it off now. Thanks for the snowman, by the way.
Well, thank you. Have a good evening.
You were able to hear everything okay, and the sound came through okay?
Yep, I heard everything. Thank you.
Great. All righty.